Hello, my name is Caitlin Rodriguez Rivera, and this is my Physics 20-11 video lab report for Lab 5, the Falling Slinky. Here is a table of contents where we'll begin with an introduction into some fundamental physics principles and laws, along with highlighting the system and associated surroundings in this experiment before moving to the video analysis composed by the system's movements, followed by a predictive computational model and a comparison between the experiment and the model, and wrapping up by answering some additional questions. First, I would like to briefly touch upon the procedure and purpose in this experiment, in which we recorded the motion of a stretch slinky falling from an elevation before constructing a computational model to determine the effects of gravity and potential drag on the motion of the object. The fundamental physics principle of Newton's second law relates the net interaction between system and surrounding to the change in momentum that it undergoes over a change in time. Some formulas of importance within this experiment include the position update formula and the velocity update formula, along with the gravitational force formula, the working concurrence with the initial information gathered from the system's video analysis, and properties to provide a basis for the computational model constructed. Now we will briefly touch upon drag force, which will be demonstrated in the computational model. Drag force models the existence of air resistance, in which an object falling from an elevation will be hit by an opposing force from air particles, which will continue to hit the front of an object in an effort to slow it down. This opposing force increases as the object gains more speed the longer it falls, until net force reaches zero due to the object no longer accelerating, at which point the drag force will be equal to gravitational force. Here is also the drag force equation, where B is a proportional constant, though I was able to find through trial and error by comparing the model to the graph generated by my tracker analysis. Next, I would like to discuss my video analysis created on Tracker, in which I plotted my coordinate axis to show the object falling in a negative y direction. Towards the middle on the right-hand side of the video analysis, you will see my coordinate points plotted on a position versus time graph that is sloping in a negative direction, demonstrating the object's fall, along with a table with all the values gathered during the analysis. Then I went on to create a computational model using the starter code provided from a previous lab experiment and inputting some initial information gathered from the return data of my tracker video analysis, such as my system's mass, initial position, and observed start time, along with an initial velocity of 0 since the object begins from rest. I also determined through trial and error that my drag proportionality constant must have been a very small and almost negligible value, since values 1 or greater will result in a longer time frame for the spring to begin its descent in the negative y direction after release. I also implemented some adjustments and formulas to the calculation loop that would continue until my last observed time, such as applying the momentum principle, which would update my object's velocity and position, and inputting the gravitational force equation that would go into calculating my net force. The tension formula was also included to demonstrate the spring's static location, as the tension in the coils countered the impact of gravity on the slinky, essentially canceling out the forces and maintaining position until the tension was no longer present, when the coils returned to their relaxed length at a certain time. Here is a visualization of the system's predicted motion based on the code and the computational model. It can be observed on the graph that the experiment and predictive computational model follow a similar trajectory, except towards the end when the model seems to predict a greater time interval for the spring's descent in the negative y direction. There was much experimenting with the value of the proportionality constant. However, it seemed that if I increased the value, the time frame would only increase more. This oversight may have been a result of human error, since I may not have consistently predicted the center of the object throughout its movement, given some difficulty with the clarity of the image as we stepped through the time frames, along with asserting a proper location for the coordinate plane to collect values. Now to address some additional questions. First, what does it mean? The bottom of the slinky remains stationary because, as previously mentioned, the tension force of the slinky is equal to gravitational force, and therefore the slinky is in static equilibrium since the two forces are opposite and equal. It will remain stationary with zero net force until the slinky reaches the bottom of the coils, where it will then be acted upon by gravity. The bottom of my model slinky does stay stationary just like in the video, since the time range just until the spring begins to make its descent is included in the tension part of the calculation loop. Thank you for watching.